Right, so I'm Rajan Alexander, and I'm a part-time student here, so it's been a bit of time since I passed the upgrade, and when you're part-time, everything's a bit attenuated, so I'm a bit on the older side, and PhD has been not part-time, so you do more. So today I'd like to talk about Hyperfine Tensors and conformations, and so I was really stretching for a pun, so just this will become funny in a few slides, I promise. I'm a supervisor at EVO, and closely involved by Sam and someone called Sam, you might know him from UCL, so Livingston, and Stefan Buchanan at Göttingen. So excuse my pronunciation of German, and do my best. Right. So these are some joint researchers labs. So I kind of inherited the problem a little bit from Henrik Busch's. I currently collaborate with Jason Park and a few other more senior researchers. Andreas has all the data that I used, and it's been extremely helpful. So just a quick shout out to those people. Right, so let's jump right in. Okay, so the physical state of electrons is determined by quantum numbers. There's three originally kind of proposed, and then a fourth that was discovered in an experiment about 100 years ago, which arises between the nuclear spin and an electron in the vicinity of the nucleus of an atom. The phenomenon that it arises is called Hyperfine coupling, and there are spectroscopy experiments called ENDOR and others that measure the hyperfine tensor is called to what's basically a spectra. So you basically set up your molecule, you paint it with some EM radiation, you paint it with another set of EM radiation, and you get an output of kind of hyperfine intensity as a function of frequency. And beyond that, I'll defer to my supervisor to make that more accurate. Molecular conformation is a spatial formation of atoms in a molecule, and what you get is hyperfine tensors, or effects that are felt at certain positions of the molecule that are sensitive to the conformation of the molecule. And just to make this more clear, I brought a model. So this is a model of the tyrosine molecule in question that is kind of the focus of our study. And it's pretty interesting because at room temperature, the bond lengths and the angles are considered stable. They don't vary very much. So the only thing that is allowed to change the conformation or the shape of this molecule is the kind of freedom of movement around single bonded atoms. And that movement is called movement around a dihedral angle. So that twist is a conformation. So of course, this molecule can exist in space, but up to kind of, if you got kind of quotient out the rotations and the translations, and you kind of take any two conformations and then kind of push them to the same spot and orient them the same way. Maybe take something stable like this benzene ring. Then the only difference you'll see in the shape this molecule can take is the differences of conformations, which are dictated by these dihedral angles. In this case, one dihedral angle about the single bond here. So that's what's happening. The benzene ring, there's 6 carbons, doubly bonded, got some hydrogens coming off. Then you have oxygen, and then on that side, you've got a couple of carbons and a couple of hydrogens. So this molecule is called tyrosine. It occurs in RNA. And it's sometimes called tyrosine, probably a bit different, but it's of interest to biochemists for that reason. So this dihedral is basically it's between this guy, this atom, this atom, this atom, this atom. So you take these three atoms, you form a plane, then you take the latter three atoms, you form another plane. You take the normals to each plane, and you measure the angle between them, kind of a sine angle. It was like 8 times 2 or something. And that angle is the dihedral. So this is what we're working with. Oh, yeah. Forgot I had a slide about this. So this is essentially saying what I just said. So yeah, two planes, two normals, and then measure the angle, and that's your dihedral. Okay. Now there are a suite of methods for calculating these hyperfine tensors and other kind of quantum quantities, and they're called density functional group, or DFT. One of the pieces of software tools that is out there, it's kind of cutting edge, is called Orca. And unfortunately, to compute hyperfine tensors, paramagnetic energy in the molecule, it takes ages. It takes anywhere from hours. I've also heard that it's maybe multiple days in some cases. So we would like to develop a surrogate model, or set of models which are fast, which fit DFT well, and are mathematically sound. It has some sort of mathematical basis, potentially extendable to other molecules and other situations, and are easy to explain to statisticians or geometers or biochemists. So the data we have, so we're taking DFT data as ground truth. I know the previous slide mentioned that it could be inaccurate, but we're taking it as ground truth for the time being. There's another research thread which can kind of cast some perspective on that, but for now we take that DFT output as ground truth. So 37 symmetric 3x3 matrices. And we have one for each dihedral rotation. The dihedral rotations are from 0 to 180 degrees in approximate 5-unit increments. So in sum, we want a geometric statistical model that maps from S1 or half of the way S1 circle to symmetric matrices. And I'm saying symmetric in full generality because they're technically not positive definite, they usually are. But they're slightly, in this case, 4 of the 37 are not. They have negative line. So ever so slightly. There is a pre and post step to get around that, but I'll cover that later. Let pause for questions. Any questions? Okay, all right. Okay, now this, if it works well, the demo daemon has struck. Okay, this should be animated, and of course it isn't. Okay, well, if this were animating, these ellipsoids centered at these hydrogen atoms would kind of change orientation and morph in their kind of stretchiness. And it would change for each dihedral angle. And so as I mentioned before, the hyperfine matrices A are actually they are symmetric matrices. Okay, so if we do a little kind of basically row flip, then we can turn these matrices into positive symmetric definite matrices, in which case the eigenvalues are positive. And by eigen decomposition, you can view these positive symmetric definite matrices as basically ellipsoids, rotated eigenvalues, where each eigenvalue is occurring on the diagonal and is the same as an axis on the ellipsoid. So that might become more clear later on, but it's a good way to illustrate what's happening and the very thing we're trying to model. Some other uses for these molecules, my kids got hold of them, and you can make them into a kind of a cluster of sort of nonsensical molecules or even belts, as my daughter did. So just some fun stuff when you leave these things around. So these matrices are dominated by the eigenvalues. So this just illustrates them. You've got basically three mostly unique. I mean, these kind of intersect a little bit, but across these are readings, you've got 37 of them. And they're sinusoidal, which is a bit of a gift in the situation, because it kind of lures you in and says, okay, well, why not just ignore any highfalutin geometry and physics and just go for it? Just go with sines and cosines. Why not just do it? Okay, so if you do that and you just kind of model it element-wise, you get 6 degrees of freedom per hyperfine matrix because it's symmetric. And if you use like this form, an offset plus cosine double angle, sine double angle, you get 18 parameters. And okay, it's a good start. It's better than a random guess. And it's kind of an upper bound for our fits. But we can do that. And just as an introduction here, we're just doing the Frobenius norm, which is element-wise, basically Euclidean, square of the edges. I played a bit fast and loose with using hats and trying to drop them. This is a model. This is not the actual data. This is the predicted Hyperfine tensor. This is the actual data. So I'm just trying to implementation. We also flirted with using something called polar distance, which in some cases turns to a metric. But I'm not going to be discussing that sadly because just time.
This is just a dumb question. So the matrix is coming from data, right? Is that correct?
Yeah.
And then you have this rotation and you're trying to map into this data.
Exactly.
Okay.
So trying to get angles to map to symmetric matrices. So 37 times.
So sorry, is there one and there's 37 different angles inside the matrix, or how?
It's a rotation. It's 37 rotations of this dihedral, 5 degrees each.
But it's one angle, right? So it's 5 degrees.
Exactly. So it's like 0, 5, 10, all the way to 180, and you're measuring the hyperfine tensor, which can be visualized as positive definite symmetric matrix. They're ellipsoid at this hydrogen and this hydrogen. So you're trying to map this angle to essentially 2 ellipsoids or 2 symmetric positive also definite matrices. And then the question is, can we do better? Okay, so we take a cue from physical models. So this is semi-well-trodden road, and there are 2 approximations, or heuristics, we call them, in this situation. One applies for larger molecules, which is the dipolar approximation. That works if you're kind of the home of your radical electron is far enough away from where you want to measure your hyperfine coupling. In this case, we're not sufficiently far away. This molecule is quite small. So the rule of thumb is maybe 4 angstrom. And we figure each bond is like 1.5. So we just about made 4 angstroms, but that is something we can use for larger molecules, not for this tensor. So what we do use is the scalar approximation, which is been put in a small paper, one of these like obscure papers from like 7 years ago, that just survives. And he basically did some quantification work. And I think I understood it for about a day and then quickly just. But anyway, so you get that form, this cosine squared form, which measures, which tells you the kind of the form of these eigenvalues. So the D here are the eigenvalues that we saw on the previous slide. So this model is basically saying that if you look at the eigenvalues, you are going to see something trigonometric. So this is the thing the model of diagonals. We still haven't thought about the rotational element because these ellipsoids are they're not just stretching in their axes, but they're also rotating at the same time. That's another bit. But just to look at the eigenvalues, this is we're taking a cue from this physical model. So we take a second try, and kind of cued by the McConnell equation. And then we look at the rotation of the eigenframe in the hyperfine tensor. And we use its eigendecomposition. Okay, so this is, again, just taking a cue from the McConnell equation. This is our model for our diagonals, our 3 eigenvalues. And then you have a cosine squared element, which is phase shifted and scaled and offset. And yeah, that captures that kind of ISO, the isotropic component. And then we pop that in the middle, and on either end, we take a rotation, 2 rotations. One rotation is accounting for the fact that the whole system is rotating by the dihedral angle. The hyperfine tensor is rotating, so it's kind of a change of frame. And another rotation, which takes account for the fact that the axis of rotation, which is between the 2 carbons, pointing that way, and you need another kind of intuitively, you need another rotation to account for the fact that this bond is sticking out that way. And it's a nice succinct model, and we have a decent fit. There is some expertise input that we'd like to get around, but it's a good starting point. And that was work that was done by Henrik and Ivo and others. And that's kind of the model I inherited. And then the question is, can we do better? Okay, so this is if you bring in some spectrometers and biochemists, and you say, okay, well, what additional things can we account for? So the eigenvalues fit and per the data differ by that cosine 6 alpha term. So you put that in. And then there's another bit where this axis is not quite straight. It kind of, this axis of dihedral rotation walks around a little bit. And I'm not qualified to speak on what that is, but that is what's affecting it. It's kind of a small precession. And then there's another adjustment to account for the fact that basically there's a slight wobble in this bond angle. So it means that the dihedral angle needs to be modulated a little bit in the rotation. So that's the third term. This one does very well. So we're kind of getting a sense of, you know, if you take a naive guess, you get 120 odd. If you take full kind of biochemist input, you get a much better fit. So we're kind of describing the sort of space of what's what to expect, the kind of in terms of fit. Okay, so there's the rub. We needed 20 parameters. And for a response set that's 60 unique values times 37, and we went up to 200 odd data points, 20 parameters is not great. And we also like to kind of generalize this a bit so that we don't need input from specialists. So we start with the eigenvalues, and we just take kind of a general approach. We expand out to the sixth harmonic, and I mean not fully, but we leave the fourth one out of it and a few extreme, but we concentrate on double angle and 6 times the angle, and then we kind of specialize a little bit further by eliminating the 6 harmonics, and then we specialize even more by adding these constraints in. And we have then a presto 3 more generalized Ricardo-based eigenvalue models. Okay, so we've done that to the eigenvalues. What about the eigenframes, the eigenvectors, the rotational component? And this is where everyone has to strap in a bit, because this is where we get into some of the fun stuff. So take a little excursion.
These preview dots, what are the specialists telling you? They're telling you that at these certain angles, or what are they telling you? How the specialists telling you stuff?
I mean,
What goes to use before you expect or something?
No, they're just saying, well, look, have you accounted for steric repulsive effects? I mean, the average mathematician, statistician would probably not know that. Like, if they just look at the data, like, how would you infer that? That's specialist input. This you could argue is kind of statistical, data analysis that comes out of that. And then this deviation, that's also kind of biochemical input in a sense. So, yeah, we want to kind of get around that and still obtain a decent enough fit. And we kind of, in a way that's, and also these two are very much geared towards the specific tensor molecule. We want something that kind of generalizes. So, that answers your question. But.
Well, that's not something that I can look at this molecule and say that this is some constraint I have. It means like the bubble. It needs some specialist knowledge. Not
very well so. Yeah.
Do you have data on other molecules?
Sorry?
Do you have data on other molecules?
Other molecules? Yeah. Yes, I do. Yeah.
So you can have a look at how well these things can work.
Exactly. Yeah. Let's see. Okay. So this is generalizing the eigenvalue models. And then what about the eigenframes? Okay, so here we start to do a little towards the geometry. So this, as might be familiar from calculus, you've got a bottom of 2 sheets, and you have like surfaces of revolution and all this sort of thing. It's all fine and good, surfaces. And then you want to kind of bridge into manifolds, and So this is a nice, I love the torus. I mean, everyone goes on about the sphere, but yeah, okay, it's real great. Torus is worked out. I mean, you have just so much happening here. And maybe it shows that I'm more psychologist at heart, but you can view the torus as like just existing in R3, just on its own. And you know where you are because all these points are labeled. This is, theta equals 5 degrees, and that's phi equals 10 degrees, and you just sort of know which point is labeled right there on the space. And you can also view this as a set of points that fulfills a certain algebraic equation. But when you parameterize it, you can kind of extract away the coordinates from the thing itself. So here, theta and phi or phi, they parameterize the entire torus through this equation. So all you need to do to tell where you are is by looking at a coordinate map and plugging it in, and then that puts you someplace on the manifold. And this detachment of the thing you're studying from the coordinates that tell you how to get around it, that is the basis for manifold theory, or algebra. And yeah, so this is entirely described by a little patch theta and phi from 0 to 2 pi, a little 2 pi square, and then it kind of repeats itself over and over again. So if you do like 2 pi, 4 pi, sort of end up at the same point, you just kind of go really round. Okay. So this whole chart concept, you can use this for circles or any manifoldable thing. The idea here is that I want to convey is that there has to be some agreement where there's overlap. And the next slide kind of makes that a bit clear. So as you know from your London A to Z or your UK A to Z, you actually, when you look at a snapshot of a page, you can navigate around a certain patch. And then there's some overlap to the next one. I mean, if it is a decent enough atlas. And you have to have some agreement overlap. At least some way to get from, kind of G5 to A1, the next one. And this is all about the same, is that you have to have some agreement on the glue. So you have to go from Rn, which is where our coordinates live, up to the manifold, and then back down to another Rn. And these are called coordinate functions, and together with open sets is called charts. And it provides a way of getting from Rn, nice, friendly, easy space Rn, to a wildly weird manifold, and then back down again. So this is illustrates another thing about manifolds, which they're locally Euclidean. I mean, globally they could look like whatever, but locally, if you take a smaller patch, you can create a homeomorphism, which makes that patch identical to your patch in Euclidean space. So some definitions. So we went from curves and surfaces, kind of classical differential geometry. Then we have a topological manifold. And that means that these maps are homeomorphisms. And then if we add another condition that these transition functions, okay, well, yeah, we have another condition that they're basically smooth. That is that they're infinitely differentiable. So C infinity, as it's called. Then we kind of upgrade our manifold from topological to a differential manifold or smooth manifold. And then just for kind of completeness, I'll put in that you add more equipment, then you have a Riemannian manifold. And that is one where it's not just smooth, but you can actually measure distances and areas. It's very useful because then you can start defining things like geodesics and things like that. Yeah, I won't go into that, just want to make sure I'm sticking to time. Now, Lie groups is they're basically differentiable manifolds where it's also a group. So you can take elements and multiply them. You can take inverses. So it's got a lot of equipment on it. There's like very technologically advanced things. Because the elements are, it's not just like a thing where you can have smooth coordinate functions, but you also can get from one place to another by multiplying or taking inverses. Okay. So drawing this back to the original plot, we want rotations. These rotating eigenframes of our hyperfine tensors have to be represented some way. And we did an eigendecomposition, which did this kind of rotation, eigenvalues, rotation transpose. So we want to model rotations in a kind of more mathematically informed way. So why not go to SO3, the whole space of rotations? And this is just a little blurb about how you can talk about SO3 as a Lie group. You can look at it as a regular submanifold, basically, yeah, it's just basically a way to create the space and from other spaces that are located. Yeah. And this is the classic reference, but these guys are fantastic, so I really recommend that if you've heard of that. Very more. Should I pause for questions? Okay. Okay, we also need to learn a little bit about tangent spaces. From calculus, we know about directional derivatives, but what about when we're not in Rn? We're working on these wobbly, weird manifolds. So basically what's done here is you take two salient properties or two properties of directional derivatives, you call them salient, and then you say, okay, anything on a manifold that fulfills these properties is called a derivation, and these are the things that inhabit tangent spaces on manifolds. And let's go to much detail, but I mean, there's an appeal to the coordinate chart because you have to go from the coordinate chart to the manifold and then to F. So that's something to keep in mind. We're never far away from coordinates. Okay. So this is kind of at the crux of one of the models we developed. So there's something called an exponential, which takes vectors on the tangent space and kind of lays them flat onto the manifold. There's something that Beatrice alluded to earlier, she was working with. In a Lie group, that thing is called a one-parameter subgroup. Basically, it's a fancy way of saying that if you take a vector in the tangent space and then you scale it and then exponentiate it, you get a curve. So imagine the vector is like, it has, if it's like that small, then the curve like kind of goes like that. If it's even larger, then the curve goes more fully out. And in a Lie group, that curve traces out a little subgroup in your Lie group. If you put a metric on your manifold, if you're able to put a metric on it, and it turns into a Riemannian manifold, then that exponential operator is going to cast out these curves along geodesics. So it's just, yeah, it's just so cool. And yeah, there's some fine print about Riemannian manifolds, but it's a good way to ascribe curves inside manifolds. It's kind of a canonical way to do it. Okay, so the manifold, the Lie group we're working with is SO3, the Lie group of rotations, the 3 space. So it's all this fancy talk about exponentiating and blah, 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 but how do you actually compute it? Well, you just take the matrix exponential. So this is actually not, it's not just like taking that and making it, okay, it's actually pretty good thing about that. But it means that the thing, the kind of projection down to the manifold is given by the matrix exponential. So we take rotation matrices and take the vector space in those rotation matrices that are the algebra or this Lie group, and then we exponentiate it down and we get back into the manifold. So this is a rotation matrix, and after putting in that member of the tangent space of SO3 and exponentiating it, we get another rotation matrix. So it's a good way to sort of trace out rotation matrices in SO3 with the use of just one vector. And if you take the opposite, if you take the operation in reverse, go from the manifold to the tangent space, it's called log, surprise, surprise. And compute that, you just do the matrix log on matrix groups. So this is big computation simplifier. Okay, so working with SO3, what are some key facts? The Lie group and the non-manifold, okay, this Lie algebra is called SO3, and what does it look like? It's skew symmetric matrices. And something you might have come across in your travels is the Rodriguez formula, which is you take these called Euler or like an axis angle, and x, y, z is a basically just rescale this, and alpha, suggested notation here, is an angle. Then this will make a rotation matrix. So this is not the rotation matrix. The next one should be this. And that's basically the basis for the Rodriguez formula. Okay. So here's the model. So we want to find we want to find a vector such that when we exponentiate it, we scale it and then exponentiate it, we get a bunch of matrices, rotation matrices, which are close to our rotation matrices obtained by eigendecomposing the hyperfine tensors A. Right? So we accounted for the eigenvalues, that was the sinusoidal bit. But what about the rotations of these ellipses? Well, this is how we get, an arbitrary number, 37. So we just exponentiate, we scale and exponentiate. And we use that's base point rotation and base point. Okay. See what fine print? Probably not. Okay. Okay. This is additional. There's some fine print in here. Basically, when you go out and decompose, you get this. Okay, take your positive definite symmetric matrix, I can decompose to get this. And it's equivalent to all this stuff, right? So basically, you take your any arbitrary argument decomposition. If you write, so kind of post multiply the rotation, and kind of pre and post multiply the diagonal, and then do the same thing with the other rotation, you get an equivalent argument decomposition. So it's, and depending on your point of view, it's an annoyance or it's interesting, but you get 24 of these permutations and sign changes, which when you multiply them out, they equal the same matrix. So you have to account for this. So what you end up getting is like kind of these kind of a rough field of vectors, and you have to smooth it out. And this just shows that for each of these 37 points, each eigenvector its own color, like first, second, third. You need to do a smoothing step so that it's tricky. Your sections, your sort of 24 versions times 37 are smooth as you go from each. So yeah, there's a bit extra work for you to do there. Okay, so how did it do? Did all right. So 8 parameters, pretty succinct.
Sorry, the smoothing is to do with the permutations or is it to do with something else?
It's basically it's okay. So hard to mention that without appealing to me. So it's sort of like if you have U1 and D1 as one eigendecomposed pair, and then you have U1, P something, and I as another eigendecomposed pair, precisely like this. So you get 24 of these. And this is just for angle 1. So decomposing hyperfine matrix 1, you get 24. All the way up to 37. And you get something similar. Now the problem is if you just naively follow this straight through this sort of default Python decomposition, you're going to get from these guys, you're going to get kind of wonky eigenvectors. So you have to do up a little method to go from this one to maybe this one, back up to this one, and then it goes this one, and that's a smoothing operation. And miraculously, it actually, because the data is very kind to us, there was no intersection. So you have 24 of these kind of sections. It's kind of a discrete section. And there is no, as you go from point to point, it's actually jumping. There are 23 discrete, non-intersecting ways to get through and get this kind of smooth output. So this is the data. This is where we're doing our fitting for eigenframes or rotation matrices. And yeah, different eigenvalue models. So as you go from expand more out, you get more parameters, and the fit gets better. So it did okay. I mean, yeah, did reasonably well, respectably. And what now? Okay, so there's another set of models like we did. And we took cues from the McConnell models. So the axis of rotation in this guy, as you remember, just wobbles a little bit. And the rate of rotation is not exactly 5 degrees. So we want to capture that. And this bears out in observations that we made on the data. So this next model, what it does is it takes these rotation matrices, these eigenframes, 37 of them, and it plots the axes of rotations on a sphere, and then tries to fit them with a small circle, using something called principal nested spheres. It also looks at the angle that each rotation matrix has, which is not the dihedral angle, but it's this redox, sinusoidal, and kind of pulls out these features and models them. I'll just zip through a bit, adds in some extra parameters. And what's nice about this is that you get like nearly 30 variants of this model, so you can kind of tweak things. And this one does particularly well. And this one does really well. Still doesn't beat the extended McConnell model. And it has a lot of parameters. So So next steps, so as mentioned, in response to Sam's questions, we're hoping to apply similar principles and modeling techniques to molecules that are a bit bigger, like more than one dihedral angle. We've got one that has like 9. And then another one is to take the set of DFT data as ground truth, take the simulated spectrum that comes out from Hyperfine Tensors as the ground truth. And then another one is to look at a model taxonomy, which I've done a little bit of. There's a whole other model, which is a quaternion model. So these models are vaguely equivalent and different in ways, and just to sort of get some formalism around that would be helpful. And this is a little snapshot of the bigger one that we've got data for. That's it.